So, continuing our discussion of logistic regression, I want to talk about this idea, the statistical idea of something called goodness of fit. Now, we didn't use this term explicitly in Stat 512, but we'll see we did sort of explore the underlying concepts behind goodness of fit. And more generally, goodness of fit is far more general than just logistic regression. It's a way of really approaching any type of statistical modeling technique. And what it basically is doing is it's just trying to measure how well our model fits the data, right? Is our model a good fit for the data, right? How good, what's the goodness of fit? Such tests are generally done by comparing observed values, right? That's the data, to model generated expected values, right? What we would expect to be under our model. Right, so again, it's something that we've often been doing. It's kind of like comparing observed to predicted or observed to expected, where that predicted or expected are generated via some statistical model. And by doing that, right, we're seeing how well our model, through its intermediaries, its predicted values, fits the data, right, fits the observed values. So in Stat 512, right, we had this thing called SSE, right? We had the sum of squared errors, right? If we think back to that, what was that? That was essentially, right, the square of observed minus predicted squared over that whatever n minus k minus 1. So that was comparing observed to predicted, right? What we observed, what we actually saw for y versus what we would have predicted to see for those values of x given the model that we've just fit. And r squared, of course, right, is sort of derived in part by SSE. So similarly, we could think of that as a measure of goodness of fit. So if you do a goodness of fit test, and we're going to talk explicitly about how to do that, in particular in the context of logistic regression, if you do a goodness of fit test and you conclude that your model does not fit the data well, that it is not an adequate fit for the data, what does that mean? Well, it could mean that we need more or different variables in our model. Could mean that there's outliers in our data. So let's start with this idea of perhaps needing more variables. So goodness of fit tests often test whether or not our model is too simple and hence might need other terms. In fact, we can often conceptualize the goodness of fit test as comparing our model of interest to this expanded model that is so large that it produces estimates that are exactly equal to the true values they are estimating, this kind of overfit model. This super expanded model is often referred to as a saturated model. Right, so we can kind of contrast the goodness of fit test with our overall or global tests of significance, right? The overall F test from 512, right? These global tests, the likelihood ratio tests that we've been doing in logistic regression, right? Those tests are comparing our model of interest to a model that has no variables at all. Right? So it's comparing our model of interest to a much smaller model. Goodness of fit tests are going the other direction. They're comparing our model of interest to a larger, more expansive model. Now, another possibility when we have bad fit is that maybe there's some outliers in our data that are contributing to this poor fit. We'll talk about the notion of outliers actually in next week's lecture. So for now, we're going to focus on just kind of models. And actually, we're going to start with just like what is one of the more common, or guys, two of the most common goodness of fit tests in the context of logistic regression. So before we do that, I want to make this observation that generally, for goodness of fit tests, a non-significant result indicates an adequate fit. So again, I mean, we're not supposed to be going into any particular statistical analysis with the type of bias, but it is always nice, right? When it's nice when we get to our designated model more quickly. And so in that sense, right, this is a little different than what we usually are excited about. We're usually excited when we see significance. Here, we're typically excited when we see non-significance. That means that we have a good model. Our model fits the data well. So the two most common goodness of fit tests for logistic regression are the Pearson's chi-square test and the Deviance test. Very, very, very familiar formula, right? I told you it would come back over and over again to delight us. This formula of observed minus predicted squared, right, over predicted. And that's exactly what this formula is. So here, right, we have two outcomes. That's why our sum, our innermost sum is from 1 to 2, right? All logistic regression, at least that we've studied so far, the y variable only has two outcomes. So we're summing over those two outcomes. We're summing over, right, you either have the disease or don't have the disease. And then this is just a formula where we have two categorical variables. One takes R values, one takes S values, so an arbitrary number of variables. But right, if we had a third variable, we would just add an extra sum. All we're basically saying is look at all possible combinations of categorical explanatory variables and our response variable. Look at how many observations there actually are in this particular combination. And then look at how much we would expect there to be based off of our model, right? So if you look at that formula for the IMS, right, what we're basically doing is we're generating that pi hat. That pi hat is basically, right, the probability of success, the probability of, say, getting the disease, based on our explanatory variables being, right, whatever value h is and whatever value I is. So we're using our model. We're coming up with these probabilities just like we talked about last class, right? We had a formula for estimating these probabilities. And then we're saying, okay, my model says there's a 30% chance that, right, if you're a female smoker, there's a 30% chance you're going to get the disease. So I would expect there to be 30% in my data set. I would expect there to be 30% of however many female smokers there are in my data set. Right, so that's sort of j equals 1. If we're assuming j equals 1 is the outcome we're interested in. J equals 2 is, for instance, not getting the disease. So, right, we have a predicted probability of not getting the disease, in this case 70%, and we would expect 70% of however many female smokers are in our data set to not get the disease, right? Now, again, observe, if it's a good model, then our predictions are good. Our test statistic will be small. We should hopefully see that. If our model is good, our test statistic is small, and of course a small test statistic is going to be non-significant. Now we can show for a sufficiently large sample size that this follows a chi-square distribution whose degrees of freedom are equal to k minus the number of parameters in our model. That number of parameters in our model includes the y-intercept. And k is however many of the R by S cells are non-empty, which is typically all of them, but And in the situation of small data sets may not necessarily be so. Here's a very similar goodness of fit test. So, right, the idea behind this, so the other one was sort of comparing observed by predicted by looking at their difference. This test statistic is comparing observed to predicted by looking at their ratio, right, and seeing whether or not that ratio is close to 1, right, in which case its log would be, the log of 1 would be 0. So that M term, that expected, is defined just as before. And so, right, we have a very, very similar looking formula. Again, right, if our observed is close to predicted, then that ratio is going to be close to 1. The log of it's going to be close to 0. And so we're going to be summing something up that that's going to be relatively small. All right. So I said if it's sufficiently large, right, it's going to follow this approximate chi-squared distribution. What are some nice rule of thumbs, right? The underlying theme of our class, I guess underlying sub-theme of our class. How do we define sufficiently large? There's a kind of a few different things we want to check. The first is that each of the R by S groups, or more generally all the covariate patterns, should have at least 10 subjects in it. And then if you look at all the covariate patterns broken down further by response groups as well. So like one is looking at like all like female smokers, female non-smokers, male non-smokers, right? Bullet points 2 and 3 are looking at female smokers who get the disease. Right, so we kind of add one extra layer on top. And we need all of those predicted cell counts, or actually 80% of those predicted cell counts to be 5 or more. And all the remaining ones, anyone that's not 5 or more, should be more than 2. Now, this is a nice example where if we don't have a large enough sample size, it's maybe not a big deal. So it turns out that when the sample size is too small, there's an upward bias. These test statistics tend to be overly large, which means that the only danger is that we might conclude that there's an inadequate fit to the data when in fact the fit is good. So the only danger is when we conclude an inadequate fit. So if we have a small sample size and we conclude that there is a good fit, then we're okay. All right, so let's go ahead. Let's return to the data set that we have been working with, that kind of generic male-female smoker, non-smoker data set that we were working with last week. So very familiar looking code, right? We proc logistics, still that data equals smokers from the previous lecture. There's our model statement here. I'm being very explicit. I want to model the event equals 1. That's the event of having a disease. Now to get the goodness of fit test, we use the aggregate option. However, the aggregate option requires to specify a scale. We'll talk more about like what the scale means and what it is that we're scaling in a future lecture. But for now, we actually don't want to do any scaling. It's weird that we have to tell SAS that, but nonetheless we do. So, right, we have to also include that scale equals none option. And so if we do that, we get the following output. Right, so there's our goodness of fit tests. The Deviance and the Pearson, of course, very close to one another. That will often be the case. In this case, their p-values are quite large. Being quite large indicates an adequate fit for the data. The degrees of freedom are 1. Why? Because the number of unique, in this case non-empty profiles, is 4. 2 options for sex times 2 options for smoking. So 4 possibilities. Our model, as we'll see on the next slide, has 3 parameters: a y-intercept, a slope for the sex variable, and a slope for the smoking variable. So 4 minus 3 gives us our 1 degree of freedom. So, right, not a whole lot to see. Maybe the one other thing for us to do an example of, or to kind of look through, is to verify that our sample size is large enough that the chi-square approximation is justified. Yeah, here's more output. We've seen this, I think, from last week's lecture. Yeah, so since those p-values for both tests are above 0.05, we conclude an adequate fit. We saw where the degrees of freedom came from already. That 4 minus 3, sorry, 4 minus 3. And so last thing to look at, although again, this is a little backwards. We actually should, it was convenient while we were looking at the output to talk about the results of the goodness of fit test. But before applying them, we should always check that our sample size is large enough to justify that test. So remember, there were sort of 2 things we had to look at. That we had that first bullet point, which looked at all combinations of explanatory variables. And then we had the second and third bullet point, which looked at all combinations of x and the y variable. Which means that there's 2 tables I need to look at. There's 2 tables that I need to look at. The first one is sex by smoking, and the second one is disease by sex by smoking. All right, so here's our sex by smoking table. We're looking at the actual cell counts, And we need to make sure that they're all 10 or more. So looking at them very quickly, we have 16, 16, 13, 30. All of those are greater than 10, so check. We're good. So sex by smoking by disease is ultimately going to be 2 2x2 tables. So here's the first one. This is the breakdown of sex by smoking for those who did not have the disease. And here we're looking at expected cell counts. So we have 9.6, 8.4, 6.4, 5.6. Remember, we want most of them. I believe it was 80% of them to be 5 or more. So far, so good. And then so far, so gooder. So actually, it looks like what? It looks like we have 3 of them. 3 out of 4 of them are good. So that's going to mean a total of 7 out of 8. Total of 7 out of 8, which is more than 80% still. So we're okay. Have expected cell counts more than 5. And then that one remaining one is more than 2, right? That's what we also needed. All right, so second and third criteria, 7 out of 8 of our cell counts have an expected cell count of more than 5, and then the one remaining one is more than 2. So check and check. That means that we're good. All right, so that sort of wraps up goodness of fit tests. We're going to revisit it. We're going to revisit goodness of fit tests next week. In a slightly more complex situation, right? Something you may have observed is that, right, we said last week that one of the cool things about logistic regression is that it allows the use of continuous explanatory variables. However, right, if we were astute, we might have noticed that the goodness of fit test statistics, the formulas for those things, used categorical explanatory variables. That is, those formulas wouldn't really extend. Why don't you go back and take a look at it and think about it? Those formulas would not work well. Those formulas would fall apart in the presence of a truly continuous variable. Which means that what? So that means that the goodness of fit test that we're talking about only work for categorical explanatory variables. If we have a continuous or multiple continuous explanatory variables, we're going to need to do something a little different. We'll talk about that next week. For this week, I just wanted to kind of expose us to us, kind of see the basics. We'll extend those basics next week. Now, to round out the rest of this week, I want to talk about this idea of coding our data. So remember from the example last week, actually, I guess just a few slides ago too, so from this week as well. In this data set, well, I guess actually you do have to look back to last week's notes to actually see where I actually inputted the data set. And if you look back at that data set, you'll see that I inputted it all as zeros and ones. And probably we didn't even blink an eye. Why? Because from the midpoint of Stat 512, we've become very used to working with these things. We call them dummy variables, right? We are practicing statisticians, and we're very comfortable with this idea of dummy variables or indicator variables, of coding things with zeros and ones. Not a big deal. However, we should observe nonetheless that a more reasonable person, yes, statisticians are not always reasonable, a more reasonable person might have coded these variables instead of 0 and 1. They might have coded it as yes or no, y or n. They might have coded the sex variable as male, female, m or f. Now, that's not a big deal. It's not the end of the world, right? Thanks to Stat 511, taught most likely by the great Professor Rieger, we know how to use data steps to recode these variables, right? If we try to run the proc-freq code as it's written, as we've used it, as we've typed the code so far, SAS will choke on the yes and the no. SAS is expecting something numeric. For example, 0 or 1. So what do? We recode. If it's yes or no, we can recode it 0 or 1 using data steps. That's what we did in Stat 512. It's not that hard. It can be a little bit tedious. Particularly remember that if you have a categorical variable with k outcomes, you need k minus 1 dummy variable. So if you have something like with 10 outcomes, that's 9 dummy variables. It's tedious to code that. It's time consuming. And it kind of makes our resultant data set look a little bit bloated. And so to relieve some of that tedium, to reduce some of that bloat, we're going to look at a very cool feature that is not unique to proc logistic. This feature is actually in most modeling procs, and that is the class statement. The class statement is a phenomenal time saver, but we have to be careful when we use it. And let's go through, let's explore, in this example actually, let's explore why it is that we have to be careful. So there's our data set, the same data set. I just coded it as a more reasonable person might. Instead of zeros and ones, I put female and male. I put yeses and nos. And I ran my code just like I did last week. The only difference is I'm now using that class statement. So if I tried to run this code for this data set without the class statement, I'm going to get an error. Because without that class statement, SAS is expecting something numeric. When I put the class statement, well, what SAS does is it says, okay, this is something categorical. I can convert it myself to something numeric. So it's kind of doing those preliminary data steps that we learned in Stat 512. It's kind of doing those data steps within the proc, which is very, very convenient. And so here's our output, right? There's our goodness of fit test, which we just learned. Looks the same, of course. There's a look up top, probability modeled is disease equals yes, right? Always check that you're in fact modeling what it is you intend to be modeling. Here's the rest of our output. We have our global our tests, our global overall tests. They are all significant, saying that at least one of our variables is significant. Right, just like before, we see the smoking variable is not significant. However, the sex variable is. And then there's our model equation and our odds ratios. Now, in a classroom setting, I would have us write down the model equation, and in fact, I have here. It's that what is it? It's that fourth bullet point. That's the model equation. But wait a second. What the cut the? If I compare this model equation, to the model equation from last week's lecture, that was the exact same data set, I have what looks to be a very different looking model equation. Very, very different looking, right? In fact, every one of those parameter estimates have different signs, don't they? So that thing's like all over the place. If you go back to last week's lecture and you look at the model we had without the class statement that we wrote down, you will see it's that logit function, right? Our logit function, right, for our estimated model. It's that negative 0.7011 blah blah blah. But when we use the class statement, we get a very different looking model equation. How can that be? Why? Why did we get a different model? And more importantly, should we be worried? Why is it different? And then I guess that will maybe help us answer the question as to how worried we should or shouldn't be. Why? Why? Where is this difference coming from? Time, my fellow statistical sleuths, time to get to the bottom of it. So, to see why these model equations ended up being different from one another, we need to revisit this Stat 512 topic on how to code variables. Now, in our earlier example and in Stat 512, we learned how to code variables as zeros and ones. This is called reference coding, or sometimes referred to as reference parameterization if you kind of want to sound a little fancier. But it should be observed that this is not the only way to code a dichotomous variable. By default, when we use the class statement, SAS uses something called effect coding. Now, in reference coding, we're familiar with this from Stat 512. With reference coding, we interpret parameter estimates as deviations from reference groups or categories, right? We have some reference group, right? Maybe that reference group is Westchester University. and we interpret parameter estimates for perhaps other universities, maybe Arcadia University, for example, maybe UPenn, for example, as what their GPA is above or below, right, the reference category Westchester University. That's how reference coding works. In effect coding, we interpret parameter estimates as deviations from some overall mean. So in reference coding, we're picking a reference category, right? Perhaps Westchester University, and we're looking at the other groups and seeing how they compare to Westchester. In effect coding, we're looking at the overall mean GPA of all students, and then we're looking at all the different universities to see how they compare to that overall mean. Now, what we're working with in logistic regression is this kind of weird kind of log odds. And we're looking at deviations from log odds, which is hard to kind of envision or interpret. It actually does have a little bit of a nicer, more easily digestible interpretation in like the context of like comparing means, like an ANOVA context, for example. And so if you want to actually read a little bit more about effect coding and kind of see how effect coding fits into right, a 512 type framework, then right, you could go to page 494 in our 512 textbook and kind of read up on it a little bit yourself. So I'll kind of leave that as a little kind of self-guided journey of statistical self-discovery. We can see how effect coding works, and also, right, see that this is in fact what SAS is using by looking at the class levels section of our output. Right, so here's our output. Right, we looked at that thing in the top where it said probability modeled as disease equals yes. We looked at the goodness of fit tests at the bottom, and notice sandwiched between those is class levels. And class level is where SAS is basically telling you, okay, you had a categorical variable for sex. It was female and male. I cannot perform algebraic operations on female and male. I have to first convert them to numbers, and this is how I'm converting them. I am going to treat the value female as if it's a 1. I'm going to treat the value male as if it's a -1. So that's what's being done with effect coding. It is not the 0 and 1 that we're used to seeing with reference coding. It is instead a 1 and a -1. Which in this case is going to translate to how they deviate from some overall mean. Yeah, so putting it in terms of a model equation, our model equation would look like this. Let x1 equal 1 if our patient is female. Let it equal x1 be -1 if our patient was born male. Let x2 be 1 if our patient's a non-smoker. Let x2 be -1 if they're a smoker. And then we have our following model equation, right? If you look just at the model equation, it looks the same. It's what's different is how we're defining those x's. And it is a little bit of a convention to, instead of using beta naught for the y-intercept, to use alpha as our y-intercept. So slight change of notation. So now, right, when we looked at our model equations from last class for our 4 different covariate patterns, right, that was beta naught plus beta 1, beta naught plus beta 2, beta naught plus beta 1 plus beta 2. That's kind of how we're used to seeing it. But now, right, we don't have anything zeroing out. We just have 1s and -1s. So now, right, the logit for a female non-smoker is going to be alpha plus beta 1 plus beta 2. The logit for a male non-smoker is going to be alpha minus beta 1 plus beta 2. So go back the previous slide, look at that model equation, and make sure that you could derive these logits, right? These log odd formulas based off the equation that we had last slide. So we interpret alpha as the overall mean log odds. Again, not a very real world type quality or quantity that's being interpreted there. But it does have a nicer interpretation again in like a 512 framework where we're working with actual means instead of like these log odds. Beta 1 is the deviation from the overall mean log odds attributable to sex, and then we interpret beta 2 as the deviation from the overall mean log odds attributable to smoking. So, as observed, the two different coding schemes will give us two different model equations, right? The coefficients are going to be different. Of course they're going to be different because the x's are defined differently. However, both coding schemes will, at the end of the day, give us all the same stuff in terms of what matters. They will give the same goodness of fit tests, they will give the same odds ratio estimates, and they will give us the same predicted probabilities. Now, we should observe, though, another thing that we need to be careful about is that the shortcut formula to calculate odds ratios that we learned last class is different under effect coding, right? We saw last class that for reference coding, you could just exponentiate the parameter estimate, and that would give you the odds ratio that we're interested in. That is not the case, as we will see in just a second. That is not the case for effect coding. So, let's do an odds ratio. Let's do an odds ratio for the sex variable. In particular, let's do an odds ratio of male to female. So an odds ratio of male to female. Well, I just took the log odds for, right, and again, we have to do this for comparing smokers to smokers, just like we did last week. So, right, if I look up the log odds for male smokers, I had it just a couple slides back. That was alpha minus beta 1 minus beta 2. If I want the actual odds ratios, I exponentiate that. Similarly, right, for female smokers, I exponentiate its alpha plus beta 1 minus beta 2. And now I simplify that. If I simplify that, I have e to the negative 2 beta 1. Which, if I plug all that in, I still get the 2.92. 2.92 is what we observed last week. So again, right, I get the same formula. I get the same odds ratio. But notice how I get it is not exponentiating the parameter variable, but exponentiating negative 2 times that parameter estimate. Right, in this case, it was actually a beta 1 hat that I'm plugging in there. So my best guess for beta 1. And then I'll leave it to you to repeat this exercise for non-smokers, right? So that's something you should be able to do on your own. We know the value you're supposed to be getting is 2.92. If that is not, in fact, what you get, reach out to me. Reach out to one of our graduate assistants, and of course, we'll help get you there. So yeah, same answer as last class, right? I mean, that makes sense. Coding our variable different should not change the relationship, right? This presumably true universal relationship that we're trying to discover, the actual relationship itself should be shouldn't change depending on like how we code variables, but how we get from our model to the relationship of interest does potentially vary depending on how we code our variables. And also observe that it doesn't matter how we calculate the odds ratio, right? Whether we compare male and female smokers or whether we compare male and female non-smokers, as long as there's no interaction present in our model. Now, even though odds ratios are calculated a little bit differently, right? Instead of exponentiating beta 1, we have to exponentiate -2 times beta 1. It does turn out, we kind of actually already saw this, that odds are calculated the same way. If you want the odds of something, you just exponentiate the model equation. All right, so we've observed what? We've observed that the SAS default, when using the class statement, is this effect coding. Some people like effect coding, right? There must be some that like it if it's the SAS default. I have my own personal bias towards reference coding. To me, I find reference coding a little easier to work with, a little bit more intuitive, a little bit easier to interpret. I'm going to guess that you feel the same way I do because our curriculum introduces you to reference coding first. If instead in 512 we had taught it in terms of effect coding, you'd probably feel more comfortable with that. So if we want to instead do reference coding, how? How can we override SAS's predilection for effect coding? Well, it's pretty easy. We just, in the class statement, we use a slash and we write param equals reference. So the default is param equals effect. If we want to override that default, we put param equals reference, and we can specify, you can see the notation right there, we could specify what our reference categories are going to be for each of our variables. Now, if we don't specify, SAS has some default that it uses to kind of specify itself. I can never remember what that default is, so personally, I always try to set it explicitly, just like I did in this code here. Right? And so now I look at the class level information. So anytime I'm using the class statement, I should be looking next at that class level information to make sure that SAS is coding these variables the way that I want it to. Right? And so here it's making female my reference category, and it's making non-smoker my reference category, excuse me, just like I asked it to. And then here's the rest of it. Notice, for example, now our model equation, if you write that out, our model equation now fits or is the same as the model equation from last week. Of course it is, right? Because we went back to reference parameterization to zeros and ones rather than the SAS default of 1 and -1. Easy enough? Yeah, not too bad. Just kind of something to be aware of, right? That the 0, 1 is not the only coding scheme out there. Now, from 512, we probably already know how to do this, but I thought it still might be worth doing one quick example to at the same time reinforce a lot of the other things that we've been learning and starting to perfect. Let's look at an example where we have a nominal explanatory variable with more than 2 categories. So here, let's do an example where we want to study the effect of race, and we code race as white, black, or Hispanic. and smoking, yes or no, on whether or not a pregnant mother's baby has a low birth weight. Oh, the beloved birth weight data set. Yeah, it's a rite of passage for all graduate categorical analysis students, now including yourself. So, if we have a categorical variable with 3 outcomes, then we're going to need to code that with 2 variables. Now notice this is also true for effect coding. If you have a categorical variable with 5 outcomes and you want to use effect coding, you're still going to need 4 variables. That is, you cannot get around the sort of God-given universal law that K categories needs K-1 variables to encode it. It's just effect coding will code those differently than those K-1 variables differently than reference coding will. So for reference coding, right, this is just like we did it in 512. We'll come up with some reference category, right? If maybe the majority of our data set is white, then we might use white as our reference category. And then we could create a R1 variable, race 1, which is 1 if the patient is black, or I guess in this case the mother, I shouldn't say patient, if the mother is black, 0 otherwise. And R2, our second race variable, which is 1 if the mother's Hispanic and 0 otherwise. Now, coding the dummy variables this way is equivalent to using the class statement in SAS with white as the reference category. This really is a big time saver, isn't it? Ah, man. Wish I had taught us this back in Stat 512. So here is some code, right? Class race, reference category white, smoking, reference category no, param equals reference, right? Otherwise the default's going to be effect coding. I want a model, so my y variable is a variable low. It's just going to be a 0, 1. In this case, 1 refers to a low birth weight baby. So I want to model whether or not the baby is in fact a low birth weight and look at that as a function of the mother's race and whether or not that mother smokes. Right, so here's our output. You can kind of look it over. Right, we can see that in this particular data set, what do we got? We had 181 observations that ended up being used. Of those 181 babies that were born, 56 of them were low birth weight, 125 were not low birth weight. We can see how SAS codes its variables. Right, so the column is essentially the variable. So that first column is that R1 variable. It's 1 if black, 0 if otherwise, right? So 0 if Hispanic or white. And then the second column is the second variable, and that's going to be 1 if Hispanic, 0 otherwise, 0 if black or white. There's our goodness of fit test. Our goodness of fit test, right? The p-values are both more than 0.05, indicating a good fit to our data. So that's good news. If we look at our overall tests of significance, all 3 of them well below the usual 0.05 threshold. So all 3 of those tests agreeing that at least one of our variables is useful in predicting whether or not a mother has a low birth weight baby. Now notice this is very slick. When we do this class statement, we get this type 3 analysis of effect, where how cool is that? SAS does an aggregate test of race. So race, remember, is actually technically two variables. To statistically code the concept of race, if we're letting race take three values, to statistically code that, we technically need two variables. Notice that SAS does an aggregate test on those two variables to do like this kind of test as to whether like this concept of race is significant, and SAS concludes that it is. So SAS concludes that both race and smoking both are significant. So both of those are important in determining whether or not we might expect a pregnant mother to have a low birth weight baby. And then we see under that our model equation. And then we see under that if we wanted some of our odds ratios, right? For example, our odds ratio of black to white, our odds ratio of Hispanic to white. Why to white? Because white was our reference category. Now, I do want us to observe right now, and I'm going to talk about this in more depth in just a few slides, but I want us to observe right now that we do not have an odds ratio estimate for blacks to Hispanics. Agreed? So we'll talk about ways we might get that in a little bit, but it's not part of it's not part of our output. It's not part of what SAS is handing us on a I guess I wouldn't call this a silver platter. I guess I'd call this a kind of white platter, sterile white platter. All right, so I think we talked all this through, right? We said all three global tests are significant, indicating at least one of our variables is useful. Right, our goodness of fit tests all indicated a good fit. Our follow-up test, right? Our overall test was significant. That tells us to dig deeper. When we dig deeper, we notice that both race and smoking are significant, hence useful in our model. That is the model equation if I wanted to write it down. Now, right, we can see that it is important best practice when we write our model equation down to not just write down something like X sub black or X sub Hispanic, but to also include how are we defining black? How are we defining Hispanic? How are we defining our smoking variable? Because we've seen there's more than one way to do that now. There's more than one way to feed a cat. And of course, there's more than one way to code a variable. We saw the odds ratios. We could talk briefly about their interpretations, right? So the odds ratio for black to white was 2.637. So what does that mean? It means the odds of black mothers from, right, this population under study to have a low birth weight baby are 2.637 times that of white mothers. Right? All other variables held constant, right? So assuming that they're both smokers or both non-smokers. The odds of Hispanic mothers to have a low birth weight baby are 2.745 times that of white mothers, all other variables held constant. And the odds of mothers who smoke having a low birth weight baby at 2.883, or is 2.883 times that of mothers who do not smoke, all other variables held constant. Now, as we already observed, because we chose white as our reference category, SAS only gave us the odds ratios comparing races to the reference category to white. But what if we wanted to know the odds ratios of black versus Hispanic? Well, there's a few options. There's actually technically four options because we could just use the definition of odds ratios and some algebra and other elements of our output to kind of throw numbers in a calculator and do it ourselves. But let's try to come up with options that don't involve calculators. So one pretty quick and easy option is just change our reference cell, right? So if you wanted the odds ratios of black to Hispanic, you could just change that reference. Instead of reference equals white, you could do reference equals black. Done and done. you can use contrast. So there's a contrast statement. The contrast statement is available in Proc Logistic, just as it is in many modeling procs. I believe you talk about the contrast statement in a fair amount of depth in Stat 513. So I'm not going to get into it other than just to say that it is an option. And then perhaps the easiest of them all is there's an odds ratio keyword inside Proc Logistic that will just compute all possible odds ratios. So let's zero in on this easiest option. The odds ratio keyword, as I said, shows all possible comparisons for specified variables. And even cooler, if you specify interactions, it will show you odds ratios at different levels, right? So for example, if you say there's an interaction between sex and smoking, it will show you the odds ratio of male to female for smokers, as well as the odds ratios of male to female for non-smokers. So there's our code. Looks the same, right? It's just now I'm adding that odds ratio statement. And then here is the consequent output. So now I have not just black versus white, not just Hispanic versus white, but now, thanks to the odds ratio statement, I have black versus Hispanic. You could even go further if you're so inclined. I don't know that it's worth the actual time putting together all the PowerPoints when our textbook says it better than I ever could. If I were to actually make slides on this, I would just directly plagiarize our textbook. So rather than do that, I will give our textbook its due credit and instead refer you to page 216, where our textbook goes into some of the really nice bells and whistles that you can implement through ODS graphics to get some very, very, very nice graphical representations of these odds ratios.